if are you speaking something, you can type here. I think I'm not able to hear. Hello? Hello, Apur. Can you speak again? Yeah, now I can. Yeah, I forget that. Right now I remember. Yeah, I love. Yeah, you could have sent me mail because I was extremely busy this week. So this is the reason I forgot totally. After uploading the lectures, I forgot about class mostly because this time is actually I'm busy. Most of the time I'm busy, so I forgot these things. And preparing of this preparation of this lecture also, I take some time now. Like very less time I'm taking this year because of busy schedule. And there are very less attendance. Like nobody is coming in the. And even in the assignments, whenever I'm checking, I'm not finding any good assignment submission. Only one or two most of the time. Others are, most of them are copy pasting. So this copy pasting in the assignment is going on, everything. So they are getting less marks. Some are submitting, some are just submitting code, which doesn't mean anything. That you copy your code in doc file or word file and then you send it to for evaluation of assignment. Assignment means that you need to solve that question, but people are not doing anything. So there's no enthusiasm from any of the person. That I will upload that Mac algorithm thing maybe in some time. This is the week 11 live class. So you can ask your doubt first, then I will start something. I think simple algorithm. Last time I think we missed it. I will try to write a code. I have already shared that code, so you can later you can look into it. I'll share it with everyone. Others? Nobody has any doubt? But in your assignment, it is looking like you have a lot of doubts. Even how to submit assignment, you guys don't know. So you can ask at least what to do in those things. Because I am really getting no assignment I am getting in which I am spending time to check. It is just like you have shared a code. If I look into it, it is mostly from ChatGPT. If it is from there, there is no problem. But the thing is, you should convey the message at least what you are communicating. So you can ask me questions. I'm here to solve the questions properly, not for even these classes. Sir already took lectures, so there is no point of again taking classes. Just I'm here for question answer session, and nobody is asking questions. Right now, Preeti, I don't know about the examination. Mostly, like I'll tell you this in the next live session. That how will be the exam? I don't think so that there will be some coding part in exam. But right now I don't know anything about exam, so because sir is designing it. When is your exam? Yes, 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 that's a good question. Uh, so in this assignment 12, you have to solve the assignment and then submit. Not A, B, C, D, those answers. You have to write the answers obviously, but the solution is needed in a, like, you just scan it and send it to us in assignment 12. And in assignment 11, I think there was a actually problem in assignment 9, in which nobody has solved about the temperature. So I could have already messaged you in the assignment 9, but there was a mistake from my side. So this mistake was, I have to convey that you don't need to solve the third part of that assignment. So the same part you need to solve in assignment 11. So turbulence, you understood turbulence? Started with. So should I take basics of turbulence in the next week? Because there will be some questions from turbulence in the exam as well. It's the last topic, so in these things I need to prepare. I don't remember everything. Apple. So sorry. This week it's not possible. But next week I'll take some questions and then I'll take turbulence part a bit. Because the coding part in turbulence is actually tough if you apply that. So nobody actually do it. Most of the time people use some models or some existing open form codes or something and then use it because it's complex. So while designing it is fine. Are you speaking something? Like, I'm not getting your voice. Okay. So that is a tricky part actually in the turbulence. So most of the time, uh, if you are directly solving the Navier-Stokes equation, then fine. Then there you can implement the turbulence. But as far as you are using the models like RANS or LES or anything, so in that there are models named K omega, K epsilon. These models for kinetic energy and everything. So for that, you most of the time, if you are starting, you can write code, but it is a bit rigorous process to write code. That is why I think sir doesn't give this into the assignment. So last assignment is actually a bit easy if you just read those two lectures, few lectures in the last. So those are easy. So till now, hmm it's a finite volume only right now. Right now, sir is teaching for, but yeah, you can use it for different things. But right now, whatever is taught for is finite volume because whenever you apply with this algorithm. So it's a fine. I am talking about turbulence only. So right now, whatever is has been uh, taught to you is for that finite volume. So I will wait for some more questions. If it is not there, then I will start. So from the starting lecture till now, uh, you can ask some questions so that I can cover in next lecture, or if I remember now, I can. If I know those things, I will tell you. That I will explain. I am saying you have any problem in understanding. No questions. So in exam, if questions are asked, then what will you do? So you, all of you are taking exam. Preeti, Apur, Kripal, at least you guys. You are taking, Preeti is taking. Giving the exam, Kripal is not replying. You are also taking? Okay. You are giving the exam. So, do you think that you are prepared? Because thing is, yeah, I saw Preeti's assignments, but I think Kripal's also. But Apur, I have never seen your assignments. So, what's the problem you face? So there was a theoretical assignment as well, this FEML. Okay, you got full marks. So no coding assignment you submitted till now. So others are just I told you that in the last time also. Others are just submitting codes. Sometimes they are submitting some whatever they have done. They are getting at least some marks. I am giving at least 25 marks to the one who is at least trying. So, and who is cheating, at least I am also giving to them. With warning, I am giving marks to them also. So, 10 marks I have given those some cheaters. So, though, like all of them has given the same assignment. 10 students, I think 10 has given the same assignment. Still, they got some marks. I don't want to give zero to them. That is why. You could have also submitted something. Because there are less students now submitting. Some are very good, others are just submitting at least. So I'm giving on the steps and at least on the trial basis some marks. So that at average will be fine. That when it lasts at the end. So try to submit this 11th and 12th assignment. 10th date is over. Okay, let's go through the simple algorithm now. Last Wednesday. Okay. Have you submitted? Have you submitted, Preeti? Okay. Because I remember checking your submitted assignment till assignment 9. Because there was very less, and you and Sanatha, and there was one guy also who got good marks. Only one got good marks, and you got average marks on that. Uh, So one thing I want to ask is you submitted code in that. Why you have not calculated the values and made a plot out of it? Yeah. So so why I am coming every week here for these kind of problems? No, no, no. I am saying hello. Am I audible? Yeah, I am saying that I am coming every week for this live session. So you can ask me here how to, like, if you are face. Hmm. No, no. If you just submit code, how can I point out? You just let me know. How can I point out? Like, do I need to go through everyone's code, each and every line? Is it possible? Do you think? Yeah, it's like 50 assignments are submitted. I can't go to the 50, and you guys have not written comments properly. What you have done. So I have seen some codes even, and assignment 7, I think, 7 or so. I have seen some code, some MATLAB files. I ran those MATLAB files, and there were some proper codes given in that. And although the results were not good, but I have given them very good marks. Maybe you also. I think you some. So. So that is not a problem. But if you want me to review, then at least I need some starting explanation. What is that code for? So what? Mm. But in Yeah, but in that a Fortran code is already shared. Yeah, before that also there was a assignment in which sir has given a code. Not simple algorithm. Not simple algorithm. Not from my side. I'm saying that in assignment file itself, there is a code always. In assignment 7 or 6 it was there, and then assignment 9 also I have given that code. So in that code you can look at the into the logic. Hmm. Okay, simple algorithm. Okay. But last time I shared a code of this Littleton cavity for Navier-Stokes equation solving. So simple is same. There will be differences that I know, but implementation will be same. That is why I shared it, so that you will not get any confusion in that. While writing, maybe I can make some mistake, but in that PDF file or the .m file, that is a perfect file which is running properly with the plots and all. So you can look into those plots, at least how to make the plots, how to make contours. So try to give it in, if assignment 11, try to put your efforts there. I will say, I shared simple algorithm code also now, so you can try in that. all of you can, like others who are not right now live, so they can also, if they are hearing, they can also try in that with that code. That is why I have given, so that you can at least perform something uh, in the assignments. I am a bit frustrated while I know that this coding part is already always tricky in the starting. It is a really tricky part, but some are trying. I am happy with them, but most of them are not trying. They are trying to copy paste from anyone. So there is one college, AMU. So from there, there are some copies. Assignments are coming. So around 10 assignments are coming from that institute, and all of them are same, exactly same. I have warned them last time also. If it is same this time also, I'll give zero, or I will devour them. Ask her to devour them properly, because this is not done. I am also coming and doing this thing. Nobody is asking. Like you guys are coming, others are not even coming and trying to ask, and at the end they are just copy pasting. There is no point of attending a course if you are copy pasting things. At least try to understand and then write in your own words. So at least let's have a engaging thing right today. I'm not testing your knowledge or anything. I am just for engagement. I am allowing you to speak. I am saying that why simple algorithm is used. Do anybody know? Or you can type in chat box also. Mm-hmm. But pressure is there in momentum equation. Exactly. That is what I want to know. Yeah, exactly. So dp by dt term is not there. That is why you need to use different algorithms. Others? Yeah. But yeah, you have this dp by dx term, and dp by dt term is not there. That is the more crux. Whatever you guys told is correct. Yeah, nice. So you know the algorithm. So I want to just uh, tell you in my manner, whatever I understand. Like I shared this Mac algorithm last time, how I think of it. So the neighbor terms are neglected most of the time. Last time, Apurva asked me that question, so I went through it just after the class, and it is mostly I have given some reason, but most of the books there is no reason why the neighbor terms are neglected. But this time I will cover something for that neighbor terms, why they are neglected. It is because of staggering in the velocity. Let me just look into it. what I'm going to cover today. So let's write this journal equation of convection diffusion equation. I will start from that only so that we can correlate from that. I don't think that I need to do this. This sir has already covered. Let me download the lecture notes. Yeah, this is what I'll do in my notes also. So there's no point of covering it. Again, same thing. So all of you has gone through sir's lecture. So in that you can ask me question from here the notes. There's no point of again doing it. I'll share my screen. Stop it. So in this, at there is a point in which you are getting some problem. Is there a point? Is there a point here? What you don't understand in simple algorithm? So this, I think so. Share. So let me go through that only. So think all right. Can you see my screen? That just let me know that. Other things I will not ask, and I'll finish this as soon as possible today. I'll upload some old lecture. Just let me know that you can see my screen. Okay. Well, oh, I missed it. Preeti, what you were saying that, sir, when I computed, I got 22, all 22 values. Sorry for this. I just ignored this. What you were saying? Just write it. Assignment 10 or 9. Okay, okay. So you have submitted it. Whenever I check it, so you made that plots, or do you want me to go through your code? Because I want you guys to get more marks because you are attending the lectures and everything and you are doing your more effort. So if okay, okay. So have you submitted with plots also? Okay, then I'll look into it. I'll look into if and those are correct, then I'll try to give good marks. And I'll also say to Apurv that you should also submit your assignment next week, next week, and next to next week also. Because if you don't submit, you will not get any marks. And you guys are actually smart, so you can submit it. Something you can submit it. You'll not submit some blender things. So I want more assignments this week. Because the task become easy for me if less assignments are there, but I don't want that. Okay, fine. Chal, theek hai. So okay, there in this code I'll tell you what some points are there, why I have taken some points. So some main points. Okay, so these are same, and when we solve the convection diffusion equation or momentum equation, we will take 1 by RE. Here I am saying that as new. It is nothing, it is just a variable in which 1 by RE value is saved. And here in this MATLAB we don't need to consider about double and all, but I think if you are coding in Fortran, just take care of this RE value. 1 by RE should not be like integer value. Other than this, alpha and alpha p are there. These are the relaxation factor. So relaxation factor means let me go through the video. So we will while solving, so those values u star, v star, and p dash, we supply some factor, some fraction to that, so that all of that will not solve in one time step only. So sometimes if we don't use this alpha, the flow field doesn't converge. Then only most of the time we have this alpha values. So alpha values will make sure that it helps in convergence of the solution. Convergence means when our error is less than that 10 to the minus 6. So that error reduction has been helped by this alpha values. So alpha values is directly used in the equation that or equation, or you can say this alpha u star values and v star values and p dash values. So here in the final collocated values, so these are same as previously given code. And then these comes, and these are also in a same way. Staggered variables are there. I think these I have done lot of times, why I am taking errors and everything. So these are same. Iteration is starting from 0, and this step is always same in any CFT code whichever I have submitted. Then these two also for the 2D grid is always same. Then we calculate UE, UW, UN and US, but just look into the capital and small. So here I am calculating the capital because This is a staggered variable, and we have staggered the. So staggering means. Okay, can I write here? Whiteboard. So this is, just ignore the drawing and all, but yeah, this is my thing, and here I have this east point, and in between I have small e, and here I have b. So this for the stagger, this will be the cell, and this cell will be there, and e, small e point will be the cell center. This, so this cell center we have the velocity ve, ue. So for that I have taken here this ue, which will be the 0.5 of uij. Uij means uij is here or here, plus ui plus 1j, but here just look into it, ij plus 1, as I also already mentioned last time, that this is because MATLAB is taking the let me tell here, MATLAB is taking direction from here and here. So if you change your coded language, this changes. If you are doing it in Python, this will change. If you are doing it in Fortran, this will change. C++, this will change. So this is according to MATLAB, because I am giving the MATLAB code. So these are here I is moving forward, here j is moving forward. Yeah. So just look into it. Just take care of it in your mind. You make it. Maybe I am sometimes forgot the things, but yeah, these are the things you should take care. I already told you in the last time this. So this UE is there. Then what we will do, we will apply it here and multiply it with delta x, and this AE, AW, AN and AS we will calculate. After that, what we will do, we will directly calculate the journal equation. We will apply that those values in the journal, which is AE is the combination of all A and neighbors and U neighbors, which we are doing here, and this total is coming like this. And why AE and DE is coming, all of you know, and if you don't know, right now ask. I am specifically not telling, because this AE is the let me tell, AE is the delta y or delta z, that area, and AE by small a is DE. It's a variable defined in any of the simple algorithm. Now ask question. Okay, no question. So this is same. I have not changed the variable name and all. Everything is same here. And then you start. The predicted value is coming like this from here. Then now again, when this iteration completes, then we will go for the boundary conditions, in which also we will apply the same thing, and similar equations we will solve here. Nothing for the other directions. Similarly here, and now we will correct the pressure field. So this P nu is actually P dash, so yeah, P nu is P dash, which is a combination of that P plus P star. So you can look into it and observe it more. If you have any problem in between the code, like right now I am explaining it to you, but while running, you should understand this code, because when you write your own simple algorithm code or you use it, and don't send it to me again in the assignment, I'll give you 0. So if you solve it according to you, so the problem sometimes you get the problem in between, because I have commented it out, but not in the proper manner, maybe. So here I could have written the formula, but in I have less time, so I have written it like this. Fine. So this boundary condition, when we will apply, then we will check the residuals and end the uh, loop. Then uh, it is just the algorithm part, so I'm not going through it. Just algorithm part. So these algorithm steps sir has taught in the class, so no point of again telling that. Then I have done the this plotting part. So you can take, while solving your assignments, you can take help from these. So how I have done plotting, why this plot has been done, and everything. So this is for the Lindgren cavity problem. So same solution you will get for this also. Maybe some more accurate as compared to this artificial compressibility. This will be more accurate, and you can increase the number of points, like you can increase it to 201 and see how much time it is taking to converge now. So just run it, play with it, do everything you can do, and then let me know in the mail that you understand. If you don't understand any of the line, you just let me know. I'll try to explain it more. Any of you, do you any of you have question or not? Don't have any question? Apurv, is it fine that I have gone through the code you asked me in the starting? Obviously, you have to go through it. So line by line, I don't want to go now line by line, because it's been a time I'm going through codes line by line, and it will be like a spoon feeding. If you don't understand, how will you write your own code? That is why I'm not going. You can ask me anytime in the mail. So mail I have already shared, so there's no point of that. You can mail me that this particular line or particular section I didn't understand. So what I will do, I will write in the mail that this means that, this means that. But it's a well commented code also, so there will be no problem in understanding that this has been written for this part or this part. So I have this notes of simple algorithm with me. So what I will do, I will take photo of it and share it with you. If you don't understand, if you can understand, because it's in a bad writing, but I will share it. So now I'll conclude the meeting or class, because there's very less attendance. Yeah, it's a long portion. It will take time around 4 hours or some. Sir is already taking it. He is explaining the things in turbulence. Mm, if you have any particular problem, then let me know and I'll cover it next time. Suppose you have a problem in RANs, just an example. So you just write that I have this problem in RANs. Any one of you, okay? So this problem in RANs model, you explain it in the next class. I will 100%. I will explain in a. I will try to explain in a more easy manner as compared to sir. Or take your questions in that particular topic. The whole things covering is, there's no point of doing those things. What I will do, I will share last year's class videos also with you. I have already done it. No. 28th October is your exam, and next Friday. Okay, let me see here. Next Friday is on 13th. So 13th will be the last class. 18th will be the last assignment submission thing. 20th. I'll reply on the mail. I'm available for you guys. So that will be not the job part, but means it will be just like helping thing. If yeah, you can ask. All of you can ask. But yeah, but write proper like proper question, whatever you are feeling to ask. Don't ask vague questions. So there was a guy in the starting. He asked me to solve a problem of company in which he was working. So that kind of problem I'll not take obviously, but the problem in the syllabus and whatever I have given quotes, everything I'll help 100%. Right now, no doubts. Nobody has read anything. Okay, okay. You know, sisters. I have. Why I will cover it? I don't know. When I told. Yeah, but the thing is, I want you to understand the simple algorithm first. So, turbulence. No, I don't want to cover turbulence this week. There's no point in like covering turbulence, and others don't even know about the difference in FB and FTM. That is why I'm not taking it. It will be overwhelming for a lot of people. I'll cover the main points next week. And Reynolds, this average stress thing, Rand's model. Rand's model, don't think about that much. Mm-hmm. Which in the mm, let me see what you are asking. Yeah, maybe I'm missing something. This is fine. Let me look into it, and what is it? I'll remember, then I'll let you know. If I don't remember, then it's next time I'll let you know. This time there was no plan of covering these things because this already has been covered by sir. Turbulent fluctuations. This thing? So what you don't understand in that? Okay, this. Okay, yeah. Tell me the thing. What you don't understand. So what I does do mostly, like if you ask me question, I'll look into the sir's lecture. Whatever he has covered, I'll not cover in my thing, most of the time. So yeah, you can ask me question in this. What's the problem? This is the simple equation which has been multiplied by u 2 dash. I don't remember the equation and all now, but I have to look into it. Specific question है अपूर्व, or should I cover whole thing next time? Because I don't remember these. I have to read into it. Read that. So about turbulent fluctuations equation, this is fine. So turbulent kinetic energy. So this will make the base for this k omega and k epsilon model. I think so. Yeah. So you can. Okay, that volume averaging. Yeah, yeah, that volume average equation, sometimes averaging is there. Yeah, yeah. This this term you are asking. These terms you are asking, that average. Hmm. 9. This is turbulence actually. Yeah. Yeah, these are the some complicated parts. The thing is, it is not that complicated actually. If you mm, so what I will do. Hmm. Yeah, this actually my concepts are good in these things. So what I will do is I'll cover this in a simple manner. These things, whole, not these equation maybe, but I will write something over these notes so that you will understand. Next time 13th, and you have to submit. Yeah, so then whenever I will cover after that, you can submit your week 12 assignment. It's completely fine. Yeah. Next time I'll cover it. This week I want you to understand the simple algorithm at least. Okay then? No questions? No? Let's conclude it. Okay?
Hello, all of you. I'm Ashish Bajpayee from IIT Kanpur, and this is the live session for Computational Fluid Dynamics and Heat Transfer NPTEL live session. And today is the last live session, and I think the course is totally complete and all the assignment has been done. So if you have further doubt or anything, you can contact me later also. And along with that, you can try to contact admin and user forum to for your doubts. Uh, so in previous classes, we have started with, uh, let me go to this. This is my first class where I have discussed what is CFD and all, and after that I have discussed about what I will cover. So these uh, basic conservation equation, partial differential equation, common method of discretization, finite difference method, numerical solution for parabolic period, PDE I have discussed, then finite volume method. These three things also I have discussed. And, so we were here till the center difference scheme in the previous class. Today I will discuss upwind exponential and hybrid scheme, and I will upload some of the videos later the solution of the flow field of Navier-Stokes equation later, because in this 1 hour it is not possible for me to cover all this. So like I will try to upload those videos. If anybody needs, just let me know, so that it will be useful for everyone to get the videos if it is needed. So let me wait for some time to some if somebody wants to join, and then we will start with week 12. So let me just summarize previous class in this so that we can further move. So previously, after discussing about the FDM, we have discussed unstudy 1D conduction equation solution. So here, we saw that or we learned that how to tackle the unstudied term in, and after that, after learning unstudied term and taking the how to take the source term and different these kind of uh, issues in the solution, we came to our to the position so that we can discuss about the convection diffusion problems. So convection diffusion problem uh, is the solution is necessary, like Navier-Stokes equation is also a convection diffusion problem. So if you want to solve that, you have to have some background of that. That's why we are discussing about the convection diffusion problem, in which the convection term which we are discussing right now, that convection term have that some of the parts which we need to consider to solve, because there is no pressure term in that. Along with that, like in the there is no scheme to solve the pressure term in that. And another thing is how we are considering the flow uh, for the convection diffusion problem. So let's for unstudied 1D conduction equation we have discussed. Then um, we have discussed how to give the weight factor in this. So there are three types of equation which we have discussed for unstudy, which if first is explicit, implicit, fully implicit, and Crank-Nicolson. After that, we concluded that in very fine grid, your time step becomes so small that your numerical solution take huge time to run. So we need fully implicit scheme, which I said that you can try. Then two-dimensional unsteady heat conduction equation also we have discussed, in which how to apply this implicit scheme I told you. Then under relaxation and over relaxation, which is used in different softwares and different codes to speed up the convergence or slow down the convergence to increase the chances of convergence. So it depends. I have discussed it in a uh, very elaborative manner in our previous class. Then comes convection diffusion problems. So general conservation equation we have discussed, then in which we have unsteady term, convection term, diffusion term, and source term. So this is, you can say, a parent equation of a Navier-Stokes equation, or any unsteady convection diffusion equation. So in this we discussed that we have already developed method in for discretizing the unsteady diffusion and source term, formulate the discretized equation of the form of this APTP. APVP is equal to A neighbor P neighbor plus P. So summation of this plus P. So this we have discussed all how to tackle that kind of equation. Then we have seen that how to discretize the convection diffusion equation, in which I started with these assumption that steady state problem we are considering now, because we know how to tackle unsteady term, then no source term, and 1D problem we are taking. Our governing equation is this, which is d over dx rho u phi uh, is equal to d over dx gamma d phi over dx. So in which we have discussed about the center difference scheme in the previous class, but there was some problem with the center difference scheme. So if I gave you some examples in which in first example it is feasible, actually it was feasible, and it was uh, like it was in the limit. But in the example 2, what we have seen is it was not physically realistic or not non-feasible. Why it was non-feasible? So these are the issues with the central difference scheme, in which this Paclet number should be less than 2 for center difference scheme to work properly. Otherwise, one of the coefficient will become negative, and if it is became negative, it means that advection scheme should not be too high relative to diffusive strength if we define Paclet number as this. So this mod of Paclet number should be less than 2 for center difference scheme to work correctly. Center difference scheme will work well if if uh, if it is Paclet number is between -2 to 2, then it will work properly. For zero diffusion or negligible diffusion problem also, we can see that it is undefined because AP is 0, so this will become undefined. And center difference scheme doesn't work at the limit of very weak diffusion. Very weak diffusion or zero diffusion, negligible diffusion, or any name you can give it to it. So there we need to apply something called as upwind scheme. Okay, we will discuss why center drawback should be overcome. Okay, why it is required. So let's come to today's class, in which I will discuss about the up. Just a minute. So the main drawback of the center difference scheme we just discussed, in which it was due to the use of linear profile assumption for advective term, where we defined this Fe phi is equal to Fe. We have taken a average between these two values of between the neighbor values for P. We have taken a average, but is it correct always? It is not. For weak diffusion, suppose one of the examples I am giving for weak diffusion, suppose this value is dominating, so it should be near to this value, but we are taking an average, and that average will make this value different than this value. So uh, if it is a weak diffusion and this is high, so it should be near, this P should be near to this is my point. And let's discuss further. In case of convection, the value of interface should be more strongly influenced by the upstream value, the direction from which flow comes. Thus now, like I said, that it should be more influenced by from the point where the flow is coming. Like suppose flow is coming from here, so it should be more influenced by this W value. Okay, so this is the basis of upwind scheme. Upwind means flowing in the direction of that particular flow in which the flow is moving. So for upwind scheme, so this is very crude way of defining it, but let's say that direction of flow is from P to E. Okay, this P to E, this direction of flow is there. Then I will define phi P or phi E, this E as phi P. And if the direction is flow is from E to P, from this direction, in this direction, then Fe is less than 0. Okay, strength is less than 0. Then phi E is equal to this capital E. So I am talking about this. So capital E. We can define it in a more systematic manner here. This Phi E is equal to Phi P maximum of Fe and 0. So what would be the maximum of Fe and 0? If Fe is positive, and Fe is positive in this condition, if Fe is positive, so this Fe in between Fe and 0, what will be the maximum? Fe will be the maximum. So we will have Phi P Fe is equal to Phi E, then Fe will cancel, and then Fe Phi P. So this I want to prove. Then in the same condition, I forgot to tell you that if Fe is greater than 0, then 0 will be the maximum here, so it will be 0. In the second condition, flow is moving in this direction. Fe is less than 0. Fe is less than 0, so it is negative than 0. So 0 is higher, so this term will become negative 0. And here it is negative, negative Fe, negative, and negative is outside also, then it will become positive Fe. So positive and total positive. The positive value is greater than 0. So this value will come out and this will become Fe into Phi max of Phi is equal to Phi Fe. So this will come, and this capital E. Okay. Same with this grid. Okay. Same procedure can be followed in this. Now, we are considering the same equation which we have considered in the previous class, which is d phi over dx, or d rho u phi over dx is equal to, this is 1D steady state equation. So, convection diffusion equation, in which we have this convection term and this diffusion term. We are just doing an integration from west to east. So this integration from west to east we are doing, and d over dx is equal into rho u phi is equal into dx is equal to west to east d over dx gamma d phi over dx. So this integration we need to perform. It is the same procedure which we did for center difference scheme. Same procedure I am following. I will just follow. I will just change where I need to uh, change for phi. That step I need to change. Other steps would remain same. So I will take this rho u phi at E minus rho u phi at W is equal to gamma d phi over dx at E eastern and gamma d phi over dx at western. So Fe phi E minus Fw phi W is equal to, so this rho u at E is Fe into phi E, rho u at W is Fw, means the convectional strength, or you can say this. Uh, so then gamma E delta Xe. What is delta Xe? Delta Xe is this. Delta Xe. Sorry for the sound coming. So delta Xe phi E minus phi P. So this becomes delta Xe, and then phi E minus phi P. So what is this? D phi E minus phi P. So in this we are taking, and then from this phi P minus phi W I will take, phi P minus phi W I will take, and what it will become at the end is Fe phi E minus Fw phi W is equal to dE. So this gamma E by delta X is dE phi E minus phi W minus dW phi P minus phi W. Okay, so this will become dW. Now comes the equation which we need actually for every term. Now comes that equation, AP phi P is equal to AE phi E AW phi W. Okay, then in this equation, what is AE, AP, and AP, AW, and AE? So AE is when we segregate, AE will become DE plus maximum of minus FE comma 0. AW will become DW plus maximum of FW comma 0. And AP will become DE plus DW. So this we will add, and this maximum of this. So we will just do a reconsideration of this, in which we will make this maximum of 0 FE comma 0 to 0 comma minus FE plus FE, so that it will become 0 at the end. And similarly, we will do for this, and we will make this positive, and FW negative will be out at outside. So this will remain the same. Just to make it more clearer, I want to make it so that because it is this, I want to make it in the AE and AW form. I am changing this. So AP is equal to now DE plus maximum of 0 comma minus FE is AE, and dw plus maximum of 0 comma fw is aw. So yes, this is aw and this is ae. So so this is now done. Okay, so no negative coefficient. So as we have discussed, Scarborough criteria is satisfied here, and scheme is more robust. This upbuild scheme I am talking about, upbuild scheme is more robust and can be used for various Peclet number. It is not restricted from -2 to 2 Peclet number. It can be used for different Peclet number. Sometimes it overestimates the effect of diffusion when the grid size is not so one condition I want to tell, that if the grid size is less in this, then we can say that it is predicting correctly. But if the grid size is bigger, then it overestimates the effect of diffusion sometimes. Okay. Sorry for the disruption. So there are some examples I want to discuss so that you can more follow these things. So the example we have discussed in the previous class, in which so let me discuss that first. So what was that example? Yes, this example in which FE and FW was we have taken it as 1, sorry 5, and DEW as 1, and so same example I am taking here. So yes, it's the same example. Then AE is equal to D here, according to center difference scheme I am calculating. It was coming as this. So VP was not physically realistic in that. Now let's see here with the upwind scheme, will it be realistic or not, and what's the difference between those two? So as we have seen here, AE is DE plus maximum of minus FE comma 0. So let's see what is it. AE is equal to DE, DE is 1, so 1 plus maximum of minus 5 comma 0. What is maximum of minus 5 comma 0? It is 0. So AE will become 1. One thing done. Okay. So now AW is DW plus maximum of FW comma 0. Okay, FW is 5. Maximum of FW comma 0 is 5 at the end. So we will have 5 here and 1 here. DW is 1. So 1 plus 5 is 6. So AW is 6. AE is 1. Done. So AP is equal to AE plus AW. 1 plus 6 is equal to 7. Now let's see what is this into the equation and what is phi p now. Phi p is AP. So AP yes, AP is 7 here. So 7 into phi p is equal to 1 into 2. AE is 1 into 2 plus 6 into 1 is equal to 8 by 7. So 8 by 7 will become, what is 8 by 7? Let me calculate it. So 1 point something, 1.1. Okay. So it is near to 1 value, near to 1 value. Okay. This is physically realistic. Now we can say why. As values of phi p is between phi e and phi w. What is value of phi e and phi w? Let me write it here. Or I have written. No. So eastern 2 and 1 and this. So this is 1.1. It is near to this value and 1.1. So our value is 1.1 near to this, which is correct. Like because the flow is coming from here, so it should be near to this value, and this value should be given the higher weightage right now. So it is between those two values. One thing proves it that it is a feasible value, physically realistic thing, and then phi p is near to phi w, which is near to 1, and which is in according to the flow direction also. So which means that this direction or this point p has more influence. Oh, okay, not p, west, this western point has more influence in that. So we have seen that this equation is satisfied. There are different kind of schemes which now we can tackle or we can solve. We have discussed central difference of wind. Let's see which other kind of equations we can solve. So there can be a exponential variation also, logarithmal variation, and polynomial variation. Why we are using this kind of equation? But because we have while we have this upwind scheme, central difference scheme. Central difference scheme, we have discussed the limitations, but upwind scheme also it is valid if suppose this is having a more influence right now, okay, but the grid size is huge. If the grid size is huge, then what will happen? This has less influence on this side or this side, suppose, because grid size is high, so it will not give the accurate value. So this we can define one more thing. Like if grid size is small, we can use a wind scheme here. uh, if the flow is coming from here, okay, then value will become phi p, which I have written, represented by this black line. So this will become flat and the value will become phi p. But the flow is coming from here, then value will become phi e, and this shows the influence of flow coming. But if the grid size is high, then we have to use some kind of exponential equation, exponential variation equation, or exponential variation we need to take, logarithmic variation, and polynomial variation. So like there can be different kind of variations, but before that I want to discuss about the some of the exact solution of this equation, where so let me define Peclet number also here. Peclet number is f by d, which is at eastern interface fe by de is equal to rho u eastern by the gamma e delta xe. So this is the Peclet number here. So I have defined this thing. So why I'm defining the exact solution, so that we will have a basic solution at least for one. So I will conclude it from here only. Okay. So for 1D convection diffusion problem, I have defined this. So now similar problem which we were discussing. So we are going to take a exact solution of those equations. Okay. So analytical solution. So this exact solution is actually the analytical solution which can be obtained for 1D convection diffusion problem without unsteady and source term. So these terms, as we have neglected previously, so now I'm also neglecting these terms so that the equation will not become more complicated. And similarly, we can solve for complex problem also. The analytical solution we can take for a complex problem, but it is really complex and sometimes very time taking. So why we are solving it gives us some physical insight about the nature of the variation of any parameter phi. So if you have an analytical problem or analytical solution, then you can analyze at any point without taking any um, so there will be no variation in that. It will be an exact correct solution of at any point. So that's why we are deriving, so that you will have some basic idea or about the nature of variation, how the phi is varying and within a control volume. Although not directly applicable to more complex problem, indirectly we understand the nature of variation of phi for complex problems also. Okay. I'm considering a domain length L as shown as I have shown here. So is phi is equal to phi 0 is the boundary conditions. Phi is equal to phi L at L x at x is equal to L. Phi is equal to phi L. Phi is equal to phi 0 at x is equal to 0. So these boundary condition I am considering. Phi varies in the control volume from phi is equal to phi 0 at x is equal to 0 to phi is equal to phi L at x is equal to L. As I have discussed, these are the boundary conditions. Now I am taking the equation, which is similar equation d over dx rho u phi is equal to d over dx gamma d phi over dx. This equation again I am considering for exact solution. So let us define the following non-dimensional term. So first, for solution of that problem, we need to define some non-dimensional term. Okay, these non-dimensional term are for solving the equation easily, you can say. So I am defining a phi star as phi minus phi 0 by phi L minus phi 0, and x star I am defining a again non-dimensional term because meter by meter will be non-dimensional. So x by L again will be x star, and phi minus phi 0 by phi L minus phi 0 is phi star. So in the non-dimensional form, let's see the boundary conditions. Boundary conditions are phi star is equal to 0 at x star is equal to 0, phi star is equal to 1 at x star is equal to 1. So now the advection term can be written as, so now I'm writing that advection term here. So d over dx over rho u, it's just the changing or putting the values here. Rho u phi is equal to rho over rho x and x star L. So let me write this. X is equal to x star L. Okay. This according to this assumption, I am writing it here. Okay. So this x will become x star L. Rho will become rho. Rho is remain the rho. Rho will remain the rho. U will remain the u. But phi will change. Phi, what will be phi? So I will write with another pen. Phi star rho L minus uh, phi L minus phi star. Sorry for this. And phi 0 is equal to phi. So this I will just substitute it here. Phi star phi L minus phi 0 plus phi 0, and so in between, if you have any doubt, you can ask me by stopping me, because it's just half an hour left, and after that you have exam. So it's if you know this, you can ask me doubts. So a similar term will continue rho u phi, and here I will take the L outside, and dx star over d phi star over dx star will be there, and this will become rho u will come outside, and Vl minus V0 will come outside, and this will become 0. So as rho u is a constant in a continuity condition, we are taking it outside. So similarly for the diffusion term, for the next term here, I will, so here I will just put this phi by this and substitute by phi by this and x by this, uh, and x by this. So these three terms, let's do it. So d over d over dx, gamma d phi over dx is equal to d over dx star l, x star l, and then gamma will remain gamma. Oh, sorry, gamma will remain d phi star phi l minus phi 0 plus phi 0. Okay, then dx star l. This thing we have substituted. Now let's do this as a solution or differentiation, which will become d phi star over dx star square, and yes, dx square will become, and gamma phi l minus phi 0 by l square will become this. Thus 1D convection diffusion equation can be written as, so this term I will take here, rho u phi l minus phi 0 by l d phi star by dx star is equal to gamma phi l, this term I will put phi l minus phi 0 by l square minus d square phi star by dx star square. Rho ul by this I am putting it gamma d phi over L, this will become this. So and this rho ul by this is Peclet number. I will put it as a Peclet number. Peclet number into this. This is the non-dimensional form of convection diffusion problem or equation. So P. So boundary conditions. Now we will apply the boundary condition. Phi star is equal to 0 at x is equal to 0, and phi star is equal to 1 at x star is equal to 1. So this equation, this boundary condition I will put here uh, for integration. So I will take this term here, and then d over dx star is d phi star over dx star minus p phi star is equal to 0. D phi star by dx star minus p phi star is equal to c1, where this is a constant. So I am just integrating this equation here, and then again integrating by this. So we will get this. I will take this c1 term here and again integrate it. Again integrating, I will get this term. So 1 by p log of c1 plus d phi star ln of this, and x ln of c2, and this c2 is again constant. Again I will put this p here and take the p ln c2 as another constant c3, ln c3, sorry. So ln c3 is another constant here. So ln c1 plus p phi star by c3 again, and px star. Okay, so this ln I have taken here. So what it will become, p phi star will become c3 e to the power px star minus c1. Now we will apply the boundary conditions here so that we can get the c1, c2, c3, c1 and c3. So at x star is equal to 0, what will it become? Phi star will be, okay, phi star will become 0, and what this will become, so I will just apply x star is equal to 0, then phi star is equal to 0, it is 0, then c3 e p dot 0, I mean it means it is 1, then c1, so c3 minus c1 is equal to 0, c3 is equal to c1. I will apply it here, which will become c1 and this e to the power px star minus 1 c1 and p phi star. At another boundary condition, at x is equal star is equal to 1, when x is equal to L, and phi star will become 1. So p into 1 is equal to c1 e to the power p into 1 minus 1. So I will take it. So c1 will become p by e to the power p minus 1. So I will apply it here. So this is the our non-dimensional equation, and this is the dimensional equation. I will just put X star value and phi star value. This is the solution for that convection diffusion problem, analytical solution. So this exact solution for variation of phi within a constant volume for a 1D convection diffusion problem without any source term and unsteady term, phi varies exponentially with x. Okay, phi varies exponentially with x. And another term, if we take it as variation of phi for different values of p, then p it tends to 0, then what will become? This phi star will become x star, and then we can see that variation of phi star is linear. Okay, now it's time. I think you can ask me question if you have somebody is there. If somebody is, because it is the last week, last discussion. If you want me to upload any video further for anything, I will upload in the that domain. You want to request any videos, so you can request or you can ask me to do it. I can, because I can't keep on teaching these things. What I will do is at the end I can write some mark algorithm and simple algorithm too, just for your reference. I can write it. I have those equations or those algorithms. These things should be understood, I think. And then these things I have discussed already. Simple algorithm. All the things have been discussed. This algorithm is not discussed. Okay. So let me discuss the exponential scheme also, which is based on this exact solution list. Okay. Exact solution based scheme. Exponential. So let me be clear that exponential, if you are applying, it is accurate, but it is accurate, but takes a lot of computational time. So let you should be clear if you need very accurate solution or not, and if the grid size is higher. So exponential scheme, I think where I put it. Of my listing after that. Okay, I think I have discussed that already. Okay. I don't know what to discuss now. I will write the algorithms first and it's done. Mac algorithm. For just to be complete. So first step, set up grid and boundary conditions. Second, calculate delta t using, as we have discussed, some of the criteria CFL or von Neumann criteria. So using CFL or von Neumann criteria, you can calculate the delta t. Third step is this initialization. So we have to define pressure and velocity, etc. These terms at t is equal to 0. What is the pressure and velocity at t is equal to 0? We need to define. Fourth is calculate d tilde n plus 1, means for the further time step, calculate d tilde n plus 1. Check this d tilde is less than this error or not. If yes, go to, so let me do this later. Sixth term is check this Pij pressure. For the pressure we are solving these equations, so Dij, so Dij I think everyone understood. Dij 2 delta t by delta x square plus 1 by delta y square. This check again. Then seventh check is oh, this was okay. Not this was calculation. Checking is again checking. Pij should be equal to Pij plus P dash Ij. This is the further Pij, next term Pij. Then eighth, okay, this is updating. Update it. Next is update your velocity in u and v direction. So it is for 2D. Then ninth is apply boundary conditions. So this I am writing for the reference purpose for the future, because you have it but not in this form. Near to boundary will change their boundary values, conditions due to updated velocity. 10th step is I think I missed something. 8th is updating it. Okay, yeah, I missed something. 4th, array. Okay, I think this term I missed. This is very important term, which is a calculation of u bar and where from Navier-Stokes equation. Now I'm going correct. This because this term matters. Go to 11. So If it is there, then we can directly go to 11. We don't need to follow these three. These some of the terms we don't need to go through. If this condition is following, we can directly go to 11. What is 11th term? 11th term is very, so checking for a steady state. If it has reached to steady state or not equation, then un plus 1 is equal to un, means this should be same, and then vn plus 1 is equal to vn, and 12th step will be t is equal to t plus delta t, means increment of the time step. 13 is go to 4 again. 4 is this calculation of this, and this 3 term will go in a loop. So these are the sum of the, like this is the algorithm for mac algorithm. You don't have to write. I will upload this. Let me go to simple also if I get it right now, or later I will upload simple algorithm. First I have mac. I think that's done. All the things are done. We will conclude our class from here. Also write simple algorithm at the last, and then I will. So that for at least for reference you have this p star. Yeah, but I need some background for this, so let's stop this. I will upload it later. Thank you. Thank you for attending the classes. If you need anything, so this is my email ID, ashishbajpai@gmail.com, and okay, this much is enough. You can ping me or mail me if you have any doubt in your assignment and coursework. So you can contact me anytime. I'll for sure reply for these things. And if you want me to, okay, yes, Farina, you send me some message. Also in 2D there is an, yes, you can do that analytical solution in 2D also. Okay, you can contact me later. Thank you, everyone.